Welcome, future engineers, to today's explainer. Today, we're unpacking the real-world scale and precision of industrial robotics, and we're going to use the modern automotive manufacturing process as our main case study. As you advance in your studies in mechanical robotics, it is absolutely crucial to take a step back and look at how individual robotic components scale up into these massive, perfectly synchronized systems. Honestly, the modern car factory is probably the ultimate expression of this. It's a place where raw materials are essentially transformed into highly complex machines through sheer, relentless automation.
So let's just dive right into the core engineering problem here. How exactly do thousands of individual, completely distinct parts become one perfectly engineered automobile? And we aren't just talking about bolting a few pieces together, right? We're trying to solve how thousands of parts are orchestrated perfectly through these interconnected robotic systems. It takes incredibly precise timing, advanced spatial awareness, and a totally seamless handoff between different types of robots and human operators. It's a massive three-dimensional logistical puzzle.
Here's our syllabus for today's lesson. We're going to trace the chronological evolution of robotic complexity from raw steel to a fully tested vehicle in 5 steps. 1. Forming the metal shell. 2. Robotic welding and inspection. 3. Automated coating and painting. 4. Powertrain and system integration. And finally, 5. Final assembly and testing. Let's kick things off with Phase 1. Forming the metal shell. We're beginning our case study at the very foundation of the build. Now, when we think of robotics, we usually picture delicate micro movements, right? Well, not here. Here we start with sheer, brute robotic force. The scale of this operation is just fascinating. Before a car even remotely looks like a car, massive automated cranes have to handle these giant, heavy coils of high-strength automotive steel. Those steel sheets get fed into enormous hydraulic stamping presses. You can really think of these presses as the mechanical muscles of the factory. They apply thousands of tons of pressure in a single, perfectly calculated motion to crush flat sheets into complex 3D shapes, stuff like roofs, fenders, and body panels. As engineers, you really have to appreciate the structural integrity required in designing these presses. I mean, they have to deliver catastrophic amounts of force repeatedly, all day long, without ever falling out of alignment. Moving right along to Phase 2, robotic welding and inspection. Let's see how we transition from that brute force into crazy high-speed precision, because now that metal shell needs a skeleton. The absolute crucial point here is coordination. Once those panels are stamped out, hundreds of robotic arms work simultaneously all around the vehicle. Every single robot performs a staggering number of laser welds with incredible millimeter-perfect accuracy. It's like this beautifully choreographed mechanical ballet, but, accompanied by a shower of electric sparks. Think about it. If even one robotic arm is a fraction of a second off, or just a millimeter out of position, it could collide with another arm or totally ruin the structural integrity of the car. Programming this level of collision avoidance and synchronized movement, that's literally one of the pinnacle achievements in modern industrial robotics.
But hey, in engineering, we literally never just assume a process worked perfectly. We verify. Before the chassis can even go near the paint shop, the factory relies on its robotic eyes. These are advanced blue laser scanners that act as super sophisticated optical sensors. They scan every single millimeter of the welded body in full 3D. The computers are crunching this data in real time to spot the absolute smallest imperfections, mathematically guaranteeing surface perfection. This automated quality assurance loop is so critical. Catching a tiny defect here costs pennies, but if you don't catch it until the car is fully assembled, that's going to cost thousands.
All right, on to Phase 3, automated coating and painting. With the skeleton rigorously inspected, we move into a totally different environment. Here, the engineering challenge completely shifts away from heavy mechanics and moves into fluid dynamics, chemistry, and strict environmental controls. It's a highly regulated sequential logic. First up, the body goes through multiple chemical cleaning stages. Next comes the primer application, then the actual color coat, and finally a protective clear coat. The robots doing this have to calculate exact flow rates, spray angles, and the atomization of the paint to get a perfectly even layer across some incredibly complex, curved geometries. Once it's coated, the glossy shell heads into an automated drying oven. The precision in this step is what prevents runs, drips, and thickness variations, ultimately giving you that flawless showroom finish.
Now for Phase 4, powertrain and system integration.
Okay, we are moving from the exterior shell right into the absolute heart and nervous system of the machine. This is where precision CNC machines cut foundational components like engine blocks, pistons, and cylinders. Notice the striking dichotomy of scale in robotics here. We're in the exact same facility, but the requirements are completely opposite. On one hand, you have those massive stamping presses utilizing thousands of tons of hydraulic pressure. On the other hand, you have robots and technicians assembling hundreds of transmission gears with microscopic accuracy. The transmission dictates exactly how engine power gets to the wheels, so those gears have to be perfectly aligned. It's a really profound lesson in adaptability for any robotics engineer. Your factory's automated systems have to be strong enough to lift entire cars, but delicate enough to place a single, perfectly lubricated gear into a complex housing.
Now, while the powertrain is being built, the interior is coming together at the exact same time. To give you an idea of the rapid, overlapping tasks happening here, workers and robots have to seamlessly collaborate to install all the interior components. We're talking seats, the dashboard, steering wheels, life-saving airbags, and highly sensitive digital displays. This is what transforms a cold metal shell into a comfortable, usable cabin. Automation in this stage often takes the form of assistive robotics. So you'll have a machine handle the awkward, heavy lifting of a dashboard, which frees up the human technician to make the fine, delicate connections.
And speaking of connections, think of this next step as installing the vehicle's nervous system. Modern cars, they're basically rolling supercomputers now. They require the exact routing of kilometers of electrical wiring. This massive wire harness has to be threaded perfectly throughout the chassis to connect hundreds of electronic sensors, battery systems, and ECUs, or electronic control units. A single pinch in just one wire during this automated routing could trigger a total cascade of sensor failures. Because of that, this is genuinely one of the most critical and complex spatial challenges in the entire factory. And that brings us to our final phase, number 5, final assembly and testing. Finally, we reach the culmination of this massive logistical puzzle. All the disparate mechanical, electrical, and digital systems we've just been talking about converge right onto the main conveyor. In the industry, this is often called the marriage. The engine, transmission, and suspension systems are brought up from below and perfectly mated to the chassis moving above. It is a phenomenal display of synchronized conveyor robotics. At the exact same time, robotic tightening tools are securing the wheels, the exhaust system, and the doors with perfectly computer-verified torque specs. This finalizes the physical build of the machine. But remember, as a robotics engineer, the automation absolutely doesn't stop just because the car looks finished. The completed vehicle is immediately pushed through a rigorous gauntlet of automated diagnostic tests. We're talking aggressive brake testing, high-pressure water leak tests in specialized tunnels, laser wheel alignment, emission testing, and even simulated road conditions on a rolling test bed. Only after the automated sensors and computer diagnostics give the green light do highly trained human inspectors come in to verify the paint and interior details. Once it gets that final approval, the cars are ready for global shipping using automated logistics networks of trucks, trains, and cargo ships. So, as we wrap up today's lesson and you go on to study these complex, interconnected webs of machines, I really want you to reflect on what we've covered. To go from a simple coil of steel to one of the world's most complex consumer products, everything we've looked at today represents years of relentless engineering excellence. The modern factory is an absolute marvel. But the thing is, it's constantly evolving. So I'm going to leave you with this question for your own engineering careers. Look at the incredible systems we have today. What will you automate next?